Okay, so we are ready to start talking about quantum gates. So I'm sure many of you know about classical gates, where you have a wire that carries a bit of information, and then you might have a gate like a NOT gate, which just flips the bit, or you might have a gate like an AND gate, which takes as input 2 bits, and it outputs 1 bit, which is the output bit is 1 if and only if both input bits are 1. So now, how do we think of a quantum gate? So let's start with single qubit quantum gates. So the quantum gate will take as input, so what comes in as a wire, which we think of as carrying, so we have a wire which we think of as carrying a qubit of information. And then the quantum gate performs some unitary transformation on this qubit and outputs a qubit which is in this new state. So it takes as input a qubit in some state psi and outputs a qubit in the state u psi. Okay, so let's look at examples. So our first example is a bit flip gate, which is given by this transformation x u0110. So now what does this do to what's x times 0? Well, this is just that. And as you can see, this gives us 0, 1, which is just the state 1. And similarly, x times 1 is just 1, 0, which is the basis state 0. So what x does is it flips the basis states. It maps 0 to 1 and 1 to 0. But now, of course, in general, the input to the x gate, or the bit flip gate, is going to be a superposition of 0 and 1. And so what it's going to do is it's going to map this 0 to a 1 and that 1 to a 0. And so if your input was this superposition, alpha 0, 0 plus alpha 1, 1, the output is alpha 1, 0 plus alpha 0, 1. Now, of course, there's one other thing we must do before we call this a quantum gate. We've got to verify that x is a unitary transformation. So what we must do is verify that x dagger x equal to x dagger equal to the identity. So what's x dagger? Well, x dagger is x itself. And so what we must do is verify that x squared is the identity. And that's an easy thing to do. It's a good exercise for you. Our second gate is the phase flip gate, which is given by this transformation, z. Okay, so again, let's see what's z times, what does it do to the 0 state? Well, it's just this product, which is just the 0 state. So it leaves it alone. What about the 1 state? Well, what it does to it is it puts a minus sign in front of it. Now, what's the point of this minus sign? Well, so again, if you start with a linear superposition of 0 and 1, alpha 0, 0 plus alpha 1, 1, it gets mapped to alpha 0, 0 minus alpha 1, 1. Okay, here's where something, let's see, there's something interesting to say here. Suppose you start with the plus state, which is 1 over square root 2, 0, plus 1 over square root 2, 1. What does z do to it? The phase flip gate acting on this gives us 1 over square root 2, 0, minus 1 over square root 2, 1, which is minus. And similarly, you can verify that z changes minus to plus. Okay, once again, before we say this is a quantum gate, we've got to verify that it's unitary. Okay, but again, as in the bit flip case, z dagger is just z itself. And so all we have to do is verify that z squared is the identity, and that's easy to see. Okay, now remember we said that a unitary transformation is a rotation of the space. So what kind of rotation is the bit flip? After all, it switches 0 to 1 and 1 to 0. It seems more like a reflection about this axis, about the 45-degree axis. So in what sense is it a rotation of the space? Well, remember, we are not working in a two-dimensional real space, but we are working in a complex vector space. And so that gives us more room to rotate. And in fact, what it is a rotation about this axis where imagine that you have a, although this is not the right picture, but just as an intuitive first, way of thinking about it, imagine you had a third dimension and that you were twirling this picture around this rotation axis. And so now if you rotate through 180 degrees or angle of pi, then this 0 will go, let's say, up above the plane, 1 will go below the plane, and then they'll, at some point they'll be orthogonal to the plane, and they keep rotating until 0 comes back, and it goes where the 1 state was, and 1 in the meantime replaces the 0. Okay, so that's the way to picture it. Phase flip gate, well, what does it do? Well, here's what it does. It leaves the 0 state alone, and it maps 1 to -1. And so what we are doing is we are rotating the space around this axis, the horizontal axis, through 180 degrees, and that leaves the 0 state alone, and it moves 1 to -1. In the process, what it also does is it swaps plus and minus, right? So it swaps these two. Okay. Now, the third elementary gate, and one of the most important gates, is the Hadamard transform, which looks like this. Its entries are 1 over square root 2, 1 over square root 2, 1 over square root 2, and minus 1 over square root 2. So let's again see, what does it map 0 to? So 0 goes to h of 0, which is 1 over square root 2, 1 over square root 2, 1 over square root 2, minus 1 over square root 2, times 1, 0. So that picks out this first column. Now this should be a state that you recognize. So this is the plus state. What about 1? Gets mapped to h of 1. This picks out the second column of this matrix. Again, that's the minus state. Okay, so now, as before, we must verify that this is a unitary transformation. So we want to check that h dagger h equal to h dagger is the identity. But once again, if you notice h dagger, what's h dagger? Well, complex conjugates, all the entries are real, so they stay unchanged. And then by symmetry, it's just h itself. So you must check that h squared is the identity. And that's, again, something that you can easily do here. Okay, so the fact that in all these three elementary gates we've seen, the square of the gate is identity means that if you apply the gate twice, you get back to where you started from. Okay, so in the case of the bit flip, it was clear. If you flip a bit twice, you get back to where you started from. In the case of the Hadamard, what this is telling us is that since 0 gets mapped to plus, well, if you apply the Hadamard again, plus gets mapped to 0. And similarly, 0 gets mapped to minus, minus gets mapped to 0. So this is actually something interesting. 0 gets mapped to 1 over square root 2, 0, plus 1 over square root 2, 1. 1 gets mapped to 1 over square root 2, 0, minus 1 over square root 2, 1. If you were to measure after performing a Hadamard transform, then in the standard basis, you would see 0 and 1 with equal probability, regardless of whether you started from 0 or 1. At this point, naively, you might think you lost all the information about where you started from. But in fact, that information is stored in the phase, whether it's plus or minus. And if you apply another Hadamard transform, you can recover that phase information back into the bit information. And now if you measure, you can actually tell whether you started from 0 or 1. Okay, once again, we can look at the geometrical picture of this, and we can say, what does the Hadamard transform do? What is it a rotation about? Which axis? Well, remember, it maps 0 to plus, plus to 0, 1 to minus, minus to 1. The axis is this pi over 8 axis. That's the rotation axis. And again, we are rotating about this axis through 180 degrees so that this 0 comes off the plane. Again, this is a rough picture. Plus goes under the plane, and they swap places. Okay, so finally, let's see something rather interesting. There's something rather interesting about how the Hadamard and the phase and the bit flip relate to each other. So what we saw is that what the Hadamard transform does is it swaps between 0 and plus and 1 and minus. Now what does the bit flip gate X do? Well, it swaps 0 and 1. And what does the phase flip gate do? It swaps plus and minus. So in fact, it turns out that if you want to apply a bit flip, so you want to swap 0 and 1, one way to do it is you apply the Hadamard. So now 0 has been renamed. You have done a change of basis so that instead of 0 and 1, you're working with plus and minus. But now if you want to swap plus and minus, you should apply the phase flip gate, Z. And so what you can write is that X is the same as first applying a Hadamard, then applying Z, and then applying the inverse of the Hadamard, which is the Hadamard itself. Right? Because H squared is the identity, H equal to H inverse. So what we're saying is, if we start from the bit 0, we apply the Hadamard, we get plus. We apply Z, we get minus. We apply the Hadamard, we get 1. And this is exactly like we applied X.